Hey, AP Chemsters, this is Mrs. Vanderwally bringing you another edition of The Blank Wall. We're going to start here in Chapter 11, starting off with Section 11.2. And this deals with solids, liquids, and gases, and kind of an introduction to this whole chapter, which will bring us into intermolecular forces. Hopefully after today's lab, you have a better understanding of what intermolecular forces are and how important they are when you're describing things going from the solid to a liquid to a gas stage. So the first question, this is kind of an intro thing. This is not a huge deal here, but what are some differences between solids, liquids, and gases? If you were to draw a picture of a solid, of a liquid, or gas, how would you do that? Well, this is kind of how I would do that. So hopefully you can tell I'm not really quite the artist, but over on the left is my attempt at drawing a solid, in the middle is my liquid, and over on the right is my gas. And hopefully you are relating things. If I say think of a solid, you're probably going to think of things like aluminum or copper or ice or diamonds. If I say what comes to mind when you think of a liquid, hopefully you're saying something like water, hopefully not things like alcohol. And as far as gases, you might think of oxygen gas, nitrogen gas, water vapor. So with those things in mind, do my pictures correspond with what you're thinking of? And hopefully yes. And hopefully you come up with some ideas where the solid, you can be writing this down even though I'm not, they're in a fixed position. The water is more free to move around. The gases are very free to move around. You might say that the solids are usually dense. Liquids are usually not as dense, and gases are really a lot less dense than your solids or liquids. Maybe you're also thinking of what kind of motion is involved. And typically solids, there is motion, but it's only a vibrational motion. The molecules and the atoms are just kind of like vibrating in their fixed positions. The water cup there with the water molecules, they are a lot freer to move around, and that's going to be important for a next section we're going to talk about. And gases, of course, are extremely free to move around. They're not really constricted except for by like walls or something like that. So those are some differences between your solids, liquids, and gases. Now, if you look down below at this table, there is several things that makes this very unique. So notice that this is for water, and water has many unique features, but we can still talk about certain things. Notice that the solid down here is going to be colder than your liquid, which is going to be colder than your gas. And that's true for every substance, three phases, that the solid phase is always colder than the liquid phase, which is colder than the gas phase of any substance. Notice something about the density. Notice how these densities are almost the same. They're not quite, but almost. But notice that over here, the gas phase is much less dense. And we're going to talk about that, why that would be the case. And notice that if you have 1 mole of gas, look at its volume, 30.5 liters. And this is at room temperature, okay? And notice that liquid, and notice the solid. So this is a liter. This is 1,000 milliliters make up 1 liter. So we're talking a huge magnitude difference in the volume of 1 mole. And then again, here's the molecular view. These molecules of water are kind of zooming around in the gas phase. They're pretty much randomly skeltered, helter-skelter in the liquid phase. But look at the solid phase. Look how organized and how orderly it is. And that's going to be really important. So maybe one thing you can add here, and I'll write it on the board too, is talking about the freedom of motions. So this is what I came up with. So if you want to add this, gases have a very high freedom of motion. Again, they're very much unconstricted. Liquids is not as much freedom of motion as gases, but certainly they are free to move around in the liquid phase. They can travel wherever they want in the cup, really, unless there's some attractive force nearby. But notice that the solid, it's in fixed positions, not much freedom at all. The only kind of motion involved is vibrational. So that's kind of an important idea here. Again, let's talk about this here, the densities of the solid, densities of liquid. If you recall, what is density equal? So density is equal to mass over volume. So what happens if the volume is bigger? Well, what happens to density? The density gets smaller. So if we look at ice, that the molar volume of ice is bigger than the molar volume of liquid. So that's why we have actually a less dense, or the density is smaller for ice than it is for liquid. And that's really important when we talk about why does ice float? What about your fish? Why is it important that in the wintertime the ice is on top of the pond and not in the bottom of the pond? And just one more thing, if you look at over here, you'll see all those spaces involved. And that's truly due to hydrogen bonding is why you have so many spaces. And it's all these gaps in between those molecules in their fixed positions is what allows it to have a larger volume. And you probably notice this too when you're making ice cubes in your freezer. You only put so much water in the ice cube tray because you know that it will expand as you make an ice cube. That is very unusual for most substances. This water is like roughly the only thing, not quite, but almost the only thing that actually works in this way. Most often, the solid is more dense than the liquid. So let's turn the page and see what we can do here. So let's fill out this chart as far as regular substances go. So let's fill this chart assuming it follows a normal pattern. So as far as density goes, hopefully you can still say that the gas is very low density, the liquid and the solids are high. That should not surprise you. What about the shape? So if you think of like a cube of aluminum, it holds its position. If you think about a cup of water and you move it into another cup of water, that water takes the shape of the cup. And if you have a container of gas, you can use a syringe and you can change the shape, if you will, of the container it's in, and it will be changed as well. So I wrote for the shape of a gas, not definite, the shape of a liquid, not definite, and the shape of a solid is definite. So what about the volume? Again, same idea. The gas can take up any volume. Like if it's in a syringe, you can squeeze the syringe in and decrease the volume. However, if you move the liquid from one graduated cylinder into another graduated cylinder, it's going to have the same volume as with the solid. Because it's already a fixed position, you know it's going to have a fixed volume. And so that's why I wrote again, volume of a gas is not definite. Liquid is definite and solid is definite. Now what about the strength of intermolecular forces? Hopefully you got the idea. What does inter, that prefix inter, like intercontinental, that means between. So the prefix inter means between. So intermolecular forces are between the molecule forces. So really, what are you asking for? What kind of attraction does a gas molecule have for another? Well, let me think. If a gas molecule is really far away from the other gas molecule, they don't have a lot of attraction for one another. As far as the liquids go, they are fairly close to one another, so there is a moderate, I would say, attraction. And for solids, they must be very high attraction for one another to remain a solid, so that room temperature is not enough to break this attraction for one another and go into like a liquid or something. So if it's a solid, it must have the highest attraction. So let me write that down. So already you're probably thinking, let's look at that liquid phase again. Do all liquids have the same intermolecular forces? Do they all have the same rate of attraction? And hopefully after today's lab, you could already say, well, no, they don't, because we saw that each of the 6 liquids tested in today's lab, no, they did not evaporate at equal rates at equal temperatures, if you will. And so we know that even within each phase, these intermolecular forces can vary. So let's use these ideas here to explain the following. So liquids and gases take shape of the containers while the solids don't. Okay, so if we consider the idea of this motion, liquids and gases are free to flow. They are free to move around each other, and because of this freedom, they take the shape of the containers. Solids, they have their molecules are in fixed positions, or their atoms are in a fixed position, depends on if we're talking about an elemental solid or not. And so these molecules basically just sit there. If you recall, the only motion a solid has is vibrational. It's not going to get out of its seat. So if you can just imagine like a classroom, if all the students are nice and orderly in their seats, it's a solid. Can they move within their position of the seat? Sure, they can. but that would be the idea of a fixed position. A liquid and gas would be like when the bell rings and everyone gets out of their seats and they are free to move around, spill out of the hallway if you'd like to. So that would be your liquid and your gas. So number 2, gases are compressible while liquids and solids are not. Very, very similar idea. Also, when we think about this answer, think about their proximity. So let's see what we can come up with. Okay, so gases are compressible. Why? Because they have large empty spaces between them, so you can't compress. Liquids and solids, they're already very close to each other. Go back and look at those pictures. And so if you try to compress them, there's not much empty space between the molecules, so there isn't a whole lot to compress. Same idea for gases having low density, while liquids and solids have high density. You could probably, I don't need to pause this and rewrite this. Again, you can say that gases have a great deal of empty space. So like we said earlier, if density equals mass over volume and volume is huge, then the overall density is very low. So liquids and solids, again, their density, or excuse me, their volumes are much smaller, therefore the densities are going to be much greater. So you can think about density and volume being inversely proportional. Now what about number 4? This is very similar to the lab that we had today. So what is an intermolecular force? So go back and look at the word. Intermolecular force, intermolecular attraction. The greater the attraction between the molecules, the higher the boiling point. All right, so I went ahead and I drew 2 water molecules, and I'm showing its polarity. If you remember back in the last chapter, the polarity dealt with these partial charges. So it says the greater the attraction between the molecules, so between the water molecule on the left and the water molecule on the right. So the more that attraction, that partial positive is attracted to the partial negative between those 2 molecules, the higher the boiling point. So it's going to take more energy to, in a sense, separate these 2 out. So if I were to somehow interfere with this attraction, then the gas can boil. So the stronger the attraction, the harder it is to break this attraction, and so it's going to result in a higher boiling point. So in number 5, I asked you to please watch that video on water and ice. It was called The Properties of Water. It's in Schoology. Hopefully you're able to see it. But what I did is I took a little screenshot of around a minute or 3.5 minutes on the video, and I wanted to show you this. So why is the density of the liquid water greater than the ice over here? Well, look at the ice. Here's a great pattern. Notice that the hexagonal arrangement, and that is very true. 6 sides and a hexagon. 6 sides to a snowflake too, by the way. So look at this empty space in between. It's almost like a honeycomb. And this is truly empty space. So what happens? The volume gets bigger. Now, when you break these attractions right here, right here, right here. So these water molecules now have a freedom of motion. Now they can just go zipping around however they want. They can actually get closer to one another. So notice that the space in this area is smaller than the space in the ice. For that reason, we can say that there is a lower volume, greater density. Greater volume, smaller density. All right, so how can we go between the states? I think most of you can say, well, duh, we can just add water, or excuse me, add heat, and the solid will melt into a liquid, and if we add more heat, we can make the liquid into a gas. But go ahead and take a look at this section right here. We're not talking about necessarily always heating. We can change the pressure. And for this reason, over here in problem number 2, this molecular diagram shows a sample of liquid water. Actually, no, it doesn't. This is propane. My mistake. So the question over here is propane. Shows propane. And the question is, what's going on here? Why do some of these propane molecules escape when you open up the valve? Maybe you noticed that. If you were to buy propane at Wardway, it's a liquid. But when you open up the valve, why is it a gas? Well, what are you doing? When you open up the valve, pressure goes down. Hey, look what happens when you reduce the pressure. Here, if you reduce the pressure, the liquid goes to the gas. So the liquid here goes to the gas. Why do you think that is? Well, if these molecules are not very attracted to each other, but with greater pressure, they are forced to be together. As soon as you increase the pressure, you are decreasing that force and they're allowed to escape. Finally, I'm about ready to run out of time, about 10 seconds. Which of the following below depicts the water vapor from a pot? So does the water molecule split up into hydrogen and oxygen? No.